Recall the fixed charge location problem we have already introduced. There are two part of costs we need to consider the trade-off, which is the setup cost and then the travel cost. So here we will convert this fixed charge location problem through our CA framework. So the first step we need to do is to consider the so-called infinite homogeneous problem, or IHP. So that means we need to consider all the parameters given constants. For example, let's see the setup cost, which is F, and then the unit transportation cost, alpha, and then the demand. Previously, the demand are given at each node or location. So in the infinite homogeneous problem, we will consider the demand as a density. So that means in a unit area, the total demand is H. We will also give the distance matrix. For example, let's consider the Euclidean norm. So in the infinite homogeneous problem, by symmetric properties, we have known that in Euclidean norm space, we should try to establish the facility to cover the area as round as possible. This is very intuitive. For example, we can build a facility and then cover customers within a circle. And then if we have multiple circles, the issue is that some of the area cannot be covered. So to achieve the most proximity to the circular partition of the demand, we will have, we call it hexagon tessellation. So that is each facility will cover a hexagon, and then this pattern are repetitive across the entire area, which is infinite homogeneous area. So for the easier calculation, we will just consider the hexagon approximated by a circle with the same area. So it's an approximation. So let's focus on the symmetric circles for each facility. So remember, we have three parameters to some extent to balance, which is fixed cost F, transportation cost alpha, and the demand density H. So to build the facility, we need to balance the area the facility covers and then the setup cost, the fixed cost. The reason is very intuitive. So if you build a very large facility covering a big area, and then the transportation cost will be higher, but then the number of facility you build is less, so the fixed cost is less. On the other way, if you build very dense facilities, the setup cost is high, but the transportation cost is low. So we want to find the best trade-off between these two cost terms as well. So suppose like the radius of our design of the facility is R, and then we know that this area A would be pi r square. So if we consider this is an infinite homogeneous area, we have infinite many circles. Each circle covers the area of A, serve all the customers within it. So given the service area is A, we know like the facility with a fixed cost F cover this amount of customers. Knowing the facility cost, we also need to know the transportation cost. So for the entire covering area, let's estimate the total transportation cost. The transportation cost will be equal to alpha times the distance. So we know this facility covers all possible customers within this circle. So the distance from a specific customer to the center or the facility is a random number based on the specific location. Therefore, we can try to estimate the average distance. So here, H indicates there are a certain amount of customers, the demand density in location near a specific point, and then the distance is given by the specific location, and then we will integrate all possible locations within this circle. See, the circle is denoted by A. So then this problem is converted to estimate the average distance. So let's use mathematics to calculate it. So to really calculate the average distance or the aggregated distance, we can first convert this into a polar axis. So that means we will consider a specific point with the angles theta and then the radius r. So in this way, we can calculate the aggregated distance as, here we use r a to indicate the radius of the circle, and then use small r to indicate the integrand variable. So in this integral, this r is the original radius, and then the r dr d theta is an equivalent measure to indicate the previous dx. Converts the traditional xy axis to the polar axis. So let's just calculate this integral. So this gives us the total aggregated distance without considering the demand yet. So with this expression, and together with the demand, we can get the total transportation cost within this circle will be equal to alpha times demand times this aggregated distance. So we have the transportation cost within this circle, and we know the fixed cost within this circle. And also we know like this circle has an area pi r square. So this is the cost within a particular circle, because the surface area for one facility. Let's consider this is an infinite homogeneous problem. So we need to convert the cost for each circle into the cost per area. This would be the fixed cost divided by the area, and also the transportation cost divided by the area. So this gives us, so sometimes we use the entire area as a decision variable to calibrate the total cost. So we can equivalently write this term into, and then we can calculate the optimized covering area, that means the density of the facility. So let's see, we have total cost per area based on the decision variable, which is the size of the covering area. We take the derivative. So with the first order condition, we can derive the optimum surface area for each facility A star. So this is very intuitive. As we can see, as the fixed cost increases, the surface area will increase because we want to build less facilities. And also when the demand increases or the transportation cost increases, we will have smaller surface area. That means we need to build more facilities. So we can plug in the optimum surface area for a facility and then get the optimum total cost per unit area. And also you can see this is very intuitive. When transportation cost increases or the demand increases or the facility cost increases, the summation of the total cost will be increased. And also we can see that the increasing order for the transportation cost and then the demand is higher than the fixed cost. So after we convert the problem into this infinite homogeneous continuous problem, you can see the optimum solution is now converted to find the best surface area for each facility. And then the customer assignment is also automatically determined by the covered area. So that means if you have a facility built, and then you will have a round area that all the customers will be assigned to this specific facility.